a principle which was originally created in a paper, or written about in a paper by Pat Helland, which talks about the difference between data that lives inside a service and the data which you share with other people. This basically what we're thinking about when we're thinking about data on the inside is something that we can change. We have complete control over, and that lets us iterate fast. But when we expose data out to the wider organization, it's much harder to change that data. And that might seem like a bad thing, but the reality is that that data on the outside, that data that you share with other people, is actually far more valuable to the organization as a whole. And it's this difference between these two which underlies a lot of the principles within data mesh. Microservices we talked about before, again, very similar pattern, one's for the data world, one's for the application space, and event streaming, which is, I think, one of the core fundamental sort of implementations that's kind of influenced the way that these type of big organizational data platforms have evolved, certainly over the last decade. And the reason I think, Michael, and I think this is such an important thing to think about, is that the field of data architecture really does require more discipline. Certainly, if you look at the software engineering world, if you think about the practice of software engineering and computer science, it has a huge amount of rigor. There's a huge amount that's been written about it. You can look at tenets like 12-factor apps or practices like refactoring, various different software architecture approaches, design patterns, etc. In the data space, there just isn't as much rigor. There isn't as much detail about how one should build sane architectures that scale and evolve sensibly over time. And data mesh is another one of these approaches which makes us think about how we actually build a system that can evolve and grow. So data architectures often lack the kind of rigor that we would see in software engineering. We end up with something that's kind of messy, where various different point-to-point communication channels are set up in slightly ad hoc ways. And event streaming is a really good way to sort of change the way that those relationships work, to standardize and provision data automatically. So in event streaming, we often say that we're centralizing an immutable stream of facts and decentralizing the ability, the freedom to adapt, act, and change.
Yeah, thanks, Ben, for setting the stage and covering the influences of the data mesh concept. Let us now dive into building a data mesh with event streaming and Kafka. Then I will discuss the 4 data mesh principles. Number 1, giving local autonomy to teams via data and domain-driven decentralization. Secondly, establishing a product thinking to treat data as a first-class product. Thirdly, to provide a self-serve data platform so the local domains can easily participate in the data mesh. And lastly, federated governance to tie these independent domains and data assets together so they actually mesh and interoperate. The data mesh concept has both organizational and technical dimensions. That being said, essentially, as a first look, we can think of a data mesh as a network to exchange data about the business, with nodes and connections. The nodes in the mesh are the data products. We'll learn more about them later, but for now, let's just imagine a node could be a microservice, a database, an application, etc. And the node's function is to produce and consume high-quality, locally curated data within the mesh for the benefits of other nodes. And related nodes, so to speak, are grouped into domains like inventory or shipments or orders. And the data flows from node to node and thus from domain to domain as needed.
Thanks, Michael. Let's look at the first principle, domain-driven decentralization. The objective of this particular principle, and it's actually pretty similar to principle 2 in many ways, is to ensure that data is owned by those that truly understand it. And probably the best way to understand this, or to think about this particular pattern, is to think about not the pattern, but the anti-pattern. Think about a data warehouse, the back of a company. Typical implementation here is that we have a bunch of data sources spread often towards the front. There'll be ETL jobs which are pulling data back to the data warehouse. The data warehouse often ends up cleaning up a lot of that data whilst not really understanding the data sets that well. And often those data products, for want of a better term, those source systems which are feeding data to the data warehouse, they don't necessarily behave particularly well. They don't even maybe think about their responsibility in the organization being one of vending good quality data. In the data mesh, the PAN is about ownership of a data asset given to a local team that is most familiar with it. So we don't have a centralized approach, we have this decentralized approach when there's actually many different participating parties exchanging data through this data mesh, where the owner of the data is always the one that understands that data best and actually typically will be where that data originates from. So let's take a practical example. Here we've got Alice. She's in that order service at the top. We have Joe down in the inventory at the bottom. And Joe gets some bad order data from Alice. What does he do? Well, his first option is just to try and fix that data locally. He may be able to do that, he may not, but let's say he does. He could do that. The problem is that it's just fixing it for him. And he actually potentially gets coupled to the fixes that he's applied if Alice then tries to fix it again upstream. So a much better thing to do is for Alice to fix it at source. That way everybody can benefit from the particular change. But for that to work, there's got to be a process where Joe and Alice can communicate quickly, and Alice is actually being a responsible citizen, a responsible member of the mesh who can make changes quickly and make sure that the data in the mesh is always of good quality. So the main recommendation we take from this first principle of domain-driven decentralization is to learn from DDT. Use a standard language and nomenclature for data. This is a really good litmus test. If your business users can't understand a data flow diagram, then you're probably not publishing data in the right way. It's probably too technical. That's normally the issue that occurs. So the stream of events should create a shared narrative that business users can actually understand, and that flows its way through the mesh.
So let's talk about the second principle, treating data as a first-class product. So to me, this is arguably the most important principle of the four. This principle is about product thinking. So your domain's shared data is managed as a true product. It's no longer a byproduct and an exhaust of what you're doing elsewhere in your domain. And your objective is to provide this data product in the right way so that other teams can make good use of it. So in other words, you treat the other teams as internal customers of your data. And this product thinking is really important to prevent data chauvinism, which is a risk of the first principle that Ben just covered. And that's because decentralization and granting local autonomy to domains may cause the creation of even more data silos than we had before, along with data quality problems if the origin domain only cares about itself. So what is a data product then? That sounds still a bit abstract, doesn't it? So we can think of a data product as a microservice for the data world. It is a node on the data mesh situated within a particular domain. And the role of the data product is to produce, possibly to consume, high quality data within the mesh. And then just like a microservice, it encapsulates everything it needs for its functioning. So first and foremost, it's the data that we want to share with the outside world. Secondly, the code that creates, manipulates, shares, and serves that data. And then thirdly, the infrastructure that we need to store the data and to run the code. So as you can see, it's really similar to microservices. And now before we take a closer look at the data product, let's first zoom out again to the bigger picture of the data mesh. Because a key question is, how is data shared across data products in the mesh? That is, how do we implement the links and the connections between the nodes in the network? And even visually, we can see that this interconnectivity lends itself very naturally to event streaming with Kafka. So here, data is provided to other data products through streams in Kafka. And any data product can consume via Kafka from the high-quality data streams of the other data products. So we can see here, this idea of a data mesh is really very similar to the idea of a central nervous system, where data is continuously flowing, being analyzed, processed, acted upon, and so forth. Now, we must remember that the data mesh shown here in this slide is a logical view. It's not a physical one. So if you know Kafka, you know that the reality looks a bit different and a bit better. So let's take a closer look at that. Because event streaming is not a point-to-point architecture that leads to the spaghetti mess that Ben showed in the beginning of this talk. Instead, event streaming is an architecture that decouples the producers of the data from the data consumers in a way that is highly scalable, fault-tolerant, and persistent because streams are doably stored. So here, a data product talks to other products only indirectly. And this layer of indirection is event streams in Kafka. So this setup is really write once, read many. And all a data product has to do to participate in a data mesh is to publish its public data streams. And then other data products can independently consume this data in the way they see fit. So now as a quick refresher then, let's recap the key properties of event streams in Kafka and why they are such a great fit here to build a data mesh. So here are some of the reasons. For instance, streams are real-time, so you can propagate data throughout the mesh immediately as soon as new information is available in the business. Streams are also persistent and replayable, so they let you capture both real-time and historical data with one setup. And because they are immutable, they make for a great source of record, which is useful for governance purposes. So let's get back to data products and the question of how do we get data into and out of a data product? And there are largely three main options. Number one, use event streams. We already discussed why this is a good idea in the data mesh. And just to contrast this to the other two options here, one key advantage is that they continuously import and export data as soon as new information is available in the business. Then the second option is use request response APIs, in order to request a data snapshot on demand, like a file export. And then thirdly, we can also use traditional ETL for batch import and batch export of nightly snapshots. And this gives you a fixed cadence of importing and exporting these data snapshots, but compared to the option B, there's less control for you over exactly what snapshot data you'll be working with. So how do we get existing systems and data into the data mesh? Well, with event streaming, you can quickly onboard data from existing systems and cloud services through Kafka connectors that stream data from these systems into the mesh in real time. Today, I think there are around 200 of such connectors readily available. So in most cases, you don't have to write anything yourself. So this is really a great way to set data in motion when you're bootstrapping a data mesh. So now that there is some data flowing into our data product, what's happening then? Well, really what's happening inside the data product is of no concern to the data mesh whatsoever. So apart from the team responsible for data product, everybody else in the data mesh only cares about the public data that is shared by this domain. How this public data is created internally doesn't really matter, as long as it meets criteria such as being traceable, trustworthy, have good quality, and so on. Now, that being said, the local team that needs to do the work still does care about how the data is being made. And among other interesting technologies, event streaming is also very useful to implement the insides of a data product. Naturally, you'd use streaming tools like KSQLDB or Kafka Streams to process any streaming data that enters or is created within a data product, and also for streaming data that leaves and is thus shared with the outside world in the data mesh. Likewise, if you use non-streaming systems, like classic databases or cloud storage services within a data product, you can streamify them with Kafka connectors. For example, as shown here, you can feed real-time updates into a relational database like MySQL from upstream data products to keep your database locally current with the latest business information, and any existing applications that interact with the database locally can continue to work as usual. And similarly, any changes to the database itself, like updates you're making to a customer profile, can be captured and shared automatically as event streams with the outside world in the data mesh. So this brings us to the last point here. In which way should we share our data products streams within the mesh? The two main considerations here are the use of schemas and the use of versioning. So when you publish a stream, you should use schemas with appropriate backwards and or forwards compatibility. This ensures, for instance, that when you add a new data field to a stream, that any existing consumers of that data can continue to operate without having to make any changes on their end. However, if you do need to introduce breaking changes to the schema of a stream, then use version streams. For example, if you're being required to obfuscate certain data fields moving forward, like user information, as in this example, which likely does break existing customers, then publish a new version of your stream and deprecate the original version. So to wrap up this principle, what are our further considerations and recommendations here? First and foremost, we need to realize that data on the outside is harder to change because it is being used already inside the organization by other teams, and it has the most value compared to data on the inside. And here we've already seen how we can use schemas and how we can handle incompatible schema changes with the patterns that we just described. The second recommendation is that you really want to get data in a data mesh from the source, from the origin of the data, not from any of the intermediaries. So otherwise, you really have this game of telephone where the further away you get from the origin of the data, the more corrupt and the more deteriorating the data becomes. And event streaming makes it really easy to subscribe to the data from directly the authoritative source. And then if there is a problem that you have to deal with locally in your domain, and then the point is, as Ben said at the beginning, you go ask the origin of the data to fix it at the source. And you shouldn't fix up the data locally, because again, that leads to this game of telephone that we want to prevent, because otherwise the data mesh does not scale inside an organization. And then lastly, this is more practical concern. You will probably come across some data sources or some systems that are really difficult to turn into first-class data products. And here again, consider the use of event streaming with things like change data capture, the outbox pattern, etc., to integrate those difficult sources into the data mesh. Back to you, Ben.
Thanks very much, Michael. So now we're going to move to principle 3. This is probably my favorite. I think Michael likes principle 2, but I think principle 3 is pretty awesome because it's the one that really starts to solve some significant problems. It's also the one that starts to push the boundaries of the technology that we have available today. But just to set the scene here, I wanted just to think back to a little example which I have in my past. It's going back some time, well over a decade, but I worked on a trade surveillance system in a big company. And the first thing we had to do was collect data from about 13 different systems. And the company had a messaging system in place, so it could publish events. A lot of these systems did publish events. But you could get the event stream, you also had to get the historical data. You had to be able to get this initial load of data into the database and then keep it up to date with event streams. And some of those systems allowed you to kind of hit a request that a back population be sent, but most of them you just kind of had to get this sort of flat file and try and import it into your database and then work out how the flat file snapshot compared to the event streams, which had completely different schemas and different names for each field. It's all really very complicated and quite hard also to marry up the temporal elements of this. So as a result, just getting the data into the database in a form that made sense took about 9 months. And this is not an uncommon story. You'll find this in many products, many projects across different industries. So principle 3 is very much about addressing that problem and getting data into your product instantaneously, allowing you to have a very tight feedback loop and move fast. So it's about providing central infrastructure. This part is central, unlike the other 2 principles, that provides real-time and historical data on demand, with this objective being to make domains autonomous. Just like we do in microservices, we want to be autonomous. We want to be able to execute, get the data that we want and execute at our own cadence through this type of rapid data provisioning. So if we think about consuming data from the mesh, we want to be able to consume both real-time and historical data. There's 2 kind of ways of doing this. The first one is the one that I described in the original example, where there's some way that I can get hold of a snapshot and there's some way that I can get hold of event streams and I can marry the 2 together. I basically get like the event streams and then the snapshot and put them together in my own database. That's very similar to the way that the Lambda architecture works, if you're familiar with that pattern, where you end up effectively with 2 systems, 2 sources of data at the same time, and you have to kind of deal with both. So there's definitely some disadvantages to that approach. Better approach, in my mind, is to use Kafka, maybe unsurprisingly, or the Kappa architecture, where we store our event data inside the event streams. So the data products of event data, the data will be stored inside Kafka so that it's available to anybody, both as real-time form as well as in its historical form. If you want the historical form, you just reset back to offset 0 and replay from the start. You can also use compacted topics if you want to reduce the amount of time it takes to load that initial snapshot. Likewise, if you use something like Confluent Cloud, that's a cloud-native implementation of Kafka, which provides infinite storage. So you can store these very large data sets indefinitely. So what does this look like in practice? Well, there is no real implementation of this. There's no one tool that wraps this up beautifully. Certainly as a product that you can buy, but there are a number of implementations at different companies, particularly some of the bigger internet companies that take this kind of form. So you end up with something where you've got a user interface within the company. You can go in there, you can type some some search terms, discover some schemas, start to introspect some of that data, look at the various different data types, pull event streams. In this case, we've got orders and customers. One of them's a historical data set, the other one's real time. And then we're going to apply a stream processing query. In this case, it's using KSQL to join these data sets together, pre-process them, filter out the things we're not interested in this case, Platinum clients, and deposit that in Elasticsearch for us to query. So that's moving over the boundary into our own data product. And this is kind of an implementation of the database inside out. So we can do this with the stream processor and Kafka, where Kafka is effectively that messaging system that remembers, and we can do it within event streaming database like KSQL DB. Both of these provide an implementation which can manipulate the events which are held inside the central event streaming platform, the central data mesh, and materialize them either as events or as something that we can query. And this point is actually pretty important. So if we think about this in a slightly broader context, imagine that the data mesh is actually a global data mesh that has many different nodes that sit across different continents. Where we have a data product here on the left, there are actually two types of interface that we can maintain between our data product and the data mesh. The traditional one would be events. That's the one at the top. We define a query which defines what data we're going to extract from the mesh, and then the mesh basically pokes events into our data product, into our database, into our S3 instance, whatever it might be. The other implementation is a query-based one, where we ask the data mesh to materialize a view. So, for example, we might materialize a view of orders that are for this particular customer. And then we can actually interact with the mesh with a request response paradigm. So it's much more database-like. We're asking the mesh to create a view, which we're then going to query. But it's still not quite like a central database, because every single product can create views of its own on separate instances. So it's kind of tied together, but you've still got the nice decoupling elements that you'd expect from a decentralized data system. So this actually leads to a pattern which is quite similar to the way infrastructure as code works. If you think about it, infrastructure as code is code plus some kind of container image, which ensures when we put the two things together that we get the same application every time. With a data mesh, we're actually, and this sort of this data mesh and be able to self-serve data, we'll be able to manufacture these views in a similar way. We have code, the definition of the view, a KSQL statement, whatever it might be. We have event streams, which can be historic, and we're able to provision exactly the same data each time, wherever we need it, inside our data product or inside the mesh itself. So we get this nice repeatability, and this helps us address some of the problems that Michael was talking about earlier, where data diverges in different ways, and also helps us with some of the things we're going to talk about in Principle 4. So final thing to talk about here is when we're thinking about this global data mesh, we also want to think about the Kafka instances which are involved. So the mesh is really one logical cluster. It'll actually be many different clusters, maybe cluster linked together if you've got a global implementation. If it's in one place, it could just be one. But logically, it's one big cluster. But the data product is an internal, it sits inside its own domain, its own bounded context, and it would always do what it wants to do. If it wants to have its own Kafka cluster, it has its own Kafka cluster. It's certainly not going to reuse the meshes one, so not for its internal systems. So it's important to note that all of the technology inside of the data product is going to be distinct from the mesh itself. On the cloud, this tends to be not a problem because clusters are somewhat arbitrary. You don't need physical nodes. On something like Confluent Cloud, you can use a multi-tenant cluster, which has got like zero cost effectively. So it's very easy for you to do this. And the cloud leads to this approach where it's actually very easy for us to blend together a variety of different as-a-service products to create these kind of on-demand instances and these on-demand data sets. Over to you, Michael.
Yeah, thank you, Ben. So let's talk about the fourth and last principle, which is federated governance. So like the first principle, decentralization, this principle is largely an organizational concern. The objective here is to ensure that all these independent autonomous teams and data products within the mesh can actually work together. That is, we want to ensure that the various constituents in the mesh actually mesh so that we can generate network effects for all this data that we share across the organization. And predominantly, this task is about establishing global standards like data governance, for example, and applying these across the full mesh. So even though we started with decentralization in principles 1 and 2, we now want to strike the right balance between decentralization and centralization to tie and glue everything together. So this isn't easy, and in practice, the execution will likely differ from company to company. So let's take a look at some concrete examples. So one important task is to ensure that the same data or the same data attribute is represented identically across these different domains. Otherwise, we can't join or correlate, for instance, data about our customers across the various domains like inventory, orders, and shipments. We won't have time in this talk to cover how to define and agree upon such data models. But what we can say is that once you do have them, then you can use data contracts, schemas, and schema registries to help you implement and enforce such standards throughout the data mesh. Another example is how data products should detect and recover from errors. Here, we can use common strategies like application logs, data profiling, and data lineage to unearth errors in the mesh. And streams are very useful here because they capture both live and historical data in a sequence of events, which let you identify cause and effect relationships much more easily, particularly if you can join and correlate streams from different domains, as discussed in the slide before. And then also, once you do find your errors, streams let you then recover and fix the errors by replaying and reprocessing historical data. Now, in this final example, we can see again that there are lots of streams within a data mesh, so lots of connections in the network. And these data streams may span, as Ben has shown, across systems, data centers, clouds, and so on. So for the purpose of tracking data lineage, we ideally want to cover the full mesh, so we must follow the data. Event streaming is, again, a key technology here to implement this in practice because it lets you track data in motion all the way from its origins to intermediate and to the final destinations. Now, let's talk about some further considerations for federated governance. So in my opinion, the most important recommendation that Ben and I can probably give you is to have the right mindset. Now, be pragmatic. Don't expect a governance system to be perfect. It only needs to be sufficiently good. There will always be parts of a data architecture that is not covered or that was just recently changed. So governance is really more a process than a particular piece of technology. And then lastly, we talked quite a bit about decentralization versus centralization. And governance is really on the centralized side. So while you probably want to standardize a number of things, please be aware of the downsides of centralized data models, as they will eventually become too slow to change. So if you really need something like this, use processes and tools like GitHub to collaborate efficiently, and most of all, have good luck. Back to you, Ben.
Thanks very much, Michael. So just to finish off, we wanted to talk a bit about the journey that you go through with a data mesh. There are these 4 principles, and we really see them as an evolution. You don't really start with principle 3. You're unlikely to skip principle 1. It's really a chronological process you go through: principle 1, principle 2, principle 3. Principle 4 is maybe slightly different, but the difficulty is increasing as you go from 1 through to 3. So 1 and 2 often used together. You should remember principle 1 is the data should have an owner, and that owner should be the team that creates it. And principle 2 is the data is your product. All exposed data should be good data. That's like a tenet that you take on in this world of a data mesh to ensure that the data that you've entered the organization is of good quality. So these are kind of organizational principles, and they're hard because they involve a lot of top-down management, but they are things from a technical perspective that are not necessarily that difficult. Principle 3, definitely a bit harder to get right. You need to make some technology, and event streaming helps a lot with this. This is when, from an event streaming perspective, where we start to talk about event streaming as a source of truth and some other patterns that we talked about earlier today. Finally, governance sits over the bottom there. So anything you want to add at the end, Michael?
Yeah, so as Ben just said, the data mesh is a concept, a way of thinking, and you should really approach building a data mesh in your company as a journey. You didn't have one last week, and you will not have a finished data mesh next week. So get the necessary management commitment, and then ideally start small with the first concrete use cases and iterate from there. And finally, while the data mesh is certainly a valuable concept, it's not the holy grail. The data mesh sits next to other useful concepts like microservices or DDD, which we talked about in the very beginning. And with its focus on analytical data, the data mesh is but one of the ways you can apply event streaming and Kafka to drive your business, just like you can use event streaming with microservices, for example, to implement the more operational systems. So apply these concepts in the way you see fit so that you can make technology useful in your company. So Ben and I hope that you enjoyed our session on data mesh and event streaming, and we wish you a lot of fun with the rest of Kafka Summit.